Hello everyone. So in the last lecture on feature selection, we discussed couple of common methods as our usual t-test or ANOVA f-test. Okay, so we said that for variable selection we can use those methods, and those methods are actually very widely used in microarray data analysis. What is microarray data analysis? Microarray data basically is data related to gene expressions collected on the microarray chip. So what happens is, for every person or for every animal, you have information on many genes. So the number of variables p is generally of the order 10,000 or 20,000, so something like that. Okay, it's generally of the order 10 raised to 4 or 10 raised to 5. However, if you want to study genes so extensively, you can't have a very large sample. So you may be studying say 10 cancer patients and then 10 healthy individuals. You record gene expression for all their genes and then you try to see which genes can predict cancer better, means which genes behave differently in cancer patients than the other genes. So n may be very small. Okay, so n may be of the order of 10. So this is a very unique scenario because we are generally used to this setting that n is far larger than p, whereas in this scenario p is much larger than n. So in such cases variable selection is of very much importance. You need to reduce the number of variables to make some sense out of this data. So here this t-test and f-test are used a lot. But the problem is, as soon as you carry out so many tests, for example, let me give you one scenario. So as I said, suppose you have data on 10 cancer patients and you have data on 10 healthy individuals and you have gene 1, gene 2 up to gene 20,000. Okay, so you have to have comparison between these 10 values and these 10 values for every gene. Okay, and then you see which genes are important and then you try to do some further analysis using those genes. So basically you will be carrying out 20,000 t-tests. Okay, now volume of t-tests, computationally it is okay. You can write an R code and you can carry out these 20,000 tests and you store 20,000 p-values and you see out of those 20,000 how many are less than 0.05. So computationally, okay, yeah, it requires good RAM, but still it is doable. It is not difficult. However, inferentially, does it cause any problem? Carrying out so many tests simultaneously, does it cause any problems? Can you think of something? Okay, so some of you might have guessed. See, we in statistics are never completely right. We always say that okay, we can say this with 95% confidence or 99% confidence. We never say that we are 100% confident that something will happen. Okay, so let me talk about 5% level of significance. So alpha equal to 5%. I am carrying out 20,000 tests. I know for each test there is a 5% chance that I commit type 1 error. Okay, and right now let us focus only on type 1 error, false positives, because we don't want any genes which are not really contributing to end up in our final selection list. Okay, so we are focusing only on type 1 error, we are ignoring type 2 error. Now we are focusing on type 1 error and we have 20,000 tests, each of which has 5% chance of giving us wrong conclusion in terms of type 1 error. So how many wrong conclusions are expected? So expected number of false positives, they are generally called as false positives. Why false positives? Because rejection of null hypothesis is generally called as test being positive. You have to think in terms of a medical scenario. For example, if you went and some diagnostic test, some pathological test was carried out on your blood and your test report is positive, means that particular disease is present in your body, right? So here being significant is considered as being positive. So false positive is basically the gene is not expressed differently. Expressed means you can just say the values are not different across the two groups, cancer patients and healthy individuals, but our test falsely says that they are different. Okay, so the gene is not expressed differently in two groups. However, the test concludes that they are different. However, the test rejects null hypothesis. So your null hypothesis is equality. So the test says they are unequal. So what is the expected number? 5% of 20,000. So 5% of 20,000 is how much? 5 into 200. So roughly 1,000. So basically out of your 20,000 conclusions, roughly 1,000 conclusions are going to be incorrect in terms of type 1 error. And this is not something we should be happy about, right? Not just that, people went a bit further and defined a couple of new terms. Okay, so this 5% level of significance is generally known as per comparison error rate. Okay, what do I mean by per comparison error rate? For every test, what is the error rate? That is 5%. Okay, 0.05. But when you are carrying out so many tests simultaneously, you are not just worried about per comparison error rate. People say we should be worried about something called as family-wise error rate. Okay, so what do I mean by family-wise error rate? It is probability of at least one false positive among all the tests that are carried out simultaneously or that are related in some sense. Among all the tests that a researcher is carrying out simultaneously, or they are related. May not be simultaneously, but like in a very short while of each other, so they are related. So let me introduce some notations to make our discussion a bit more concrete. Okay, so given null hypothesis, we have two possibilities. It could either be true or it could be false. On the other hand, the test can give us two outcomes. So the test can say that the difference is non-significant, or it can say that the difference is significant. Okay, so the total number of tests that we carry out can be divided into this 2x2 table. So suppose we carry out G tests. Okay, why G? Because we are talking in terms of genes. So suppose we carry out G tests, out of which for G0 null hypothesis is true, and for remaining G minus G0 null hypothesis is false. Of course, in almost 99.99% of the real life situations, your G0 and G minus G0 are unknown. You don't know how many null hypotheses are actually true. What you know is how many tests are significant. So this, let me call is R. R is total number of rejections. So the number of acceptances becomes G minus R, because total number of tests is G. So this is known, this is known, this is known. Now these can be further split into 4 numbers. Let me name them U, T, V, S. Okay. So U are actually those H naughts which are true, and the test also says they are true. So these are true negatives. Okay, these are true negatives. Then S, so these H naughts are false and the test says they are significant. So these are true positives. Now here V, here H naught is actually true, but the test says they are significant. So it is false positive and this becomes false negative. Okay. Now what does family wise error rate say? Family wise error rate says we have to see among all the G tests, what is the probability of getting at least one false positive? Okay. So let me try to first compute that and then we'll try to relate it to these numbers. Now we want probability of at least one false positive in G tests carried out, each test carried out at 5% level of significance. So let me call alpha. Okay, because the same argument would work even if alpha is 0.01. Now at least one false positive can be written as 1 minus probability of no false positive. Correct? Okay. So 1 minus. Now probability of no false positive in G tests. Right now we don't know if there is any relationship or dependence between these G tests. But for the sake of convenience, let us assume that all these tests are independent. Okay, that conclusion of one test doesn't really affect the conclusion of other test. As a result, probability of no false positive in them would be product of individual probabilities. So product over I going from 1 to G, probability of no false positive in ith test. Okay, getting it? Because we are assuming them to be independent, probability of their intersection is product of their individual probabilities. So 1 minus probability of I going from 1 to G. Now what is probability of no false positive in any given test? For a single test, probability of a false positive is alpha. That's how we define alpha. So no false positive would be 1 minus alpha. So when we take product, this would become 1 minus alpha raised to G. Okay. And now imagine G going to infinity. Because why? Because G is number of genes. It can be very large. In our case, in general, it can be any number of variables. So as G goes to infinity, what happens? 1 minus alpha is strictly less than 1. So as G goes to infinity, 1 minus alpha raised to G goes to 0. You have studied this in real analysis. If you take a raised to x, a raised to n, where a is between 0 and 1, a raised to n goes to 0 as n goes to infinity. As a result, this converges to 1. Okay. And you really don't need, even if we say infinity, in reality, we really don't need things to be infinity. Say, let me take G equal to 100. So G equal to 100, so this probability is 1 minus 0.95 raised to 100. So what is 0.95 raised to 100? It is already almost close to 0. It is 0.006. So 0.006 means what? Probability of at least one false positive is already 99.994 percent, even when G is equal to 100, where 100 is not really a large number. Getting 100 variables is very common these days. Okay. So it means that family wise error rate will almost always tend to 1. What is the meaning of that? Meaning of this is we are almost sure of committing at least one error. Remember, I am talking about only false positives. I am not talking about the type 2 error. I am talking about only type 1 error. So we are almost sure of committing at least one type 1 error. This is not really a good thing. We can't say, okay, my analysis is good if I am almost sure of committing at least one mistake. Right? So these things, so this, and as we mentioned above, expected number of false positives is alpha times g, which also goes to a very big number. So this goes on increasing, so it goes to infinity as g goes to infinity. So these two things tell me that there is a serious problem when we carry out multiple tests of hypothesis simultaneously. Okay, so these are known as multiplicity issues in testing of hypothesis. Okay, so we need some way of dealing with these issues. So what are the ways? So first let us try some simple ways. So the very first simple thing that people came up with is known as Bonferroni adjustment of p-values. Okay. Now what does Bonferroni adjustment says? Suppose I have carried out G test. So the p-values are represented by P1, P2, Pg. These are the p-values. So we adjust p-values. So adjusted, let me use another notation. So adjusted p-value for ith null hypothesis would be minimum of 1 comma g times original p-value. Okay. So what we are doing is basically we are multiplying all the p-values by the number g. But of course that can make some p-values larger than 1 and we can't have that. P-value is after all a probability. So we are taking minimum over 1 and GPI. What does it mean? What we are doing? So basically we would reject only if adjusted p-value is less than alpha, means GPI is less than alpha. So Pi is less than alpha by G. So we are making rejection region smaller. We are making rejection harder, right? Normally we reject when p-value is less than alpha. So suppose this is 0, this is alpha and somewhere towards right I have 1. So normally we reject if p-value falls in this region. Now we are making it alpha by G. So we are making rejection harder. So we reject only if p-value is in this small region. Okay. Making rejection harder makes sense because we are dealing with type 1 error. So if you make rejection harder, in general probability of rejection decreases and hence probability of rejection when H0 is true also decreases and hence probability of type 1 error decreases. So this is one simple adjustment. In fact, you might have come across this in your design of experiments course. But however, some of you might have already started thinking, what are the consequences of it? Okay, everything is going to have side effects. If I am going to make rejection too hard, that means I am going to make acceptance too easy. Okay, you have seen in BSc that type 1 error and type 2 error kind of go in opposite direction. So if I am reducing type 1 error so much, then type 2 error is bound to increase, it's bound to inflate. As a result, power of the test would go on decreasing. So that's why Bonferroni adjustment is done only if you are okay with less power. Okay. So it is one of the widely used methods, no doubt about that, but you have to remember that it does decrease the power of the test. Okay. Another method which performs slightly better than Bonferroni is known as Sidax adjustment for p-values. These are all known as p-value adjustments because they are changing p-values. So Sidax method says adjusted p-value for jth hypothesis would be 1 minus original pj raised to g. Okay. Important thing to notice that the order of the p-values is still retained. Means if you were, what do I mean by that? So if you have say pi less than pj in the original setup, then pi adjusted is also less than pj adjusted. Okay, and that should always happen. You should not end up, accepting some hypothesis which was more likely to get rejected in the earlier scenario. Okay, so this should happen with every such adjustment. So in Bonferroni it is obvious to see because you are just multiplying by G on both the sides. In SIDAX it may be slightly difficult to see, but still it is okay. I mean, it's not impossible to see. You can just write down, multiply both sides by minus sign, and remember that minus sign inverts the inequality sign, etc. And you can prove that Pi adjusted is less than Pj adjusted. Okay. So this is known as SIDAX adjustments. SIDAX adjustment is slightly better than Bonferroni in the sense it is also going to inflate your type 2 error, but comparatively it would inflate to less extent. Okay. So another third version that people came up with is known as FDR. FDR stands for false discovery rate. So people thought that okay, Bonferroni and SIDAC are good, but they are affecting type 2 error also too much. So we need something in between. Okay. So you have per comparison error rate here. You have family wise error rate here. Right. Family wise error rate is of course going to be greater than per comparison error rate, because per comparison error rate is probability of false positive in a single test, whereas this is probability of one false positive in all the tests. So of course it is larger. So what Bonferroni and SIDAC do is they try to control family wise error rate at alpha. Okay. So Bonferroni and SIDAC, both these methods adjust p-values in such a way that family wise error rate is controlled at alpha. Okay. So this is family wise error rate, and you are trying to control that at alpha, means your alpha is somewhere here to the right of family wise error rate. So from PCER you are much away. So your per comparison error rate becomes very low, and that of course triggers type 2 error to be high. So you need something in between. So this in between thing is denoted by FDR. Okay, so FDR is somewhere between per comparison error rate and family wise error rate. Let us first define these things in terms of the notations that we had introduced earlier, and then we will see how FDR is between these two, and then we'll try to see the method to control FDR. Okay, so let me see. Okay, so per comparison error rate means out of total tests, what is the number of false positives. Okay, so per comparison error rate is actually, so let me try to take this table. Okay, so per comparison error rate is what? Probability of false positive in total number of tests. So if we want to write in terms of these notations, per comparison error rate here in this table would be V upon G, number of false positives out of total number of tests. But of course V, U, T, S, everything is random, so it is expected V upon G, right? What do I mean by this? If you carry out 100 tests, each at 5% level of significance, you may not get exactly 5 to be false positives. You may get somewhere around 5. Because 5 is theoretical, whereas in sample, of course, some variations are possible. So V by G is supposed to be close to 5%. So expected V by G is exactly 5%. Okay, so this is per comparison error rate. So, and what is family wise error rate? Family wise error rate is probability of getting at least one false positive. So it is probability of V being greater than or equal to 1. Okay, at least one false positive. And V of course cannot be negative, so this is same as probability of V not equal to 0. Okay, anyway all these are counts, so they can't be negative and they can't be fraction. Okay, now FDR, false discovery rate, is defined as out of total discoveries, how many are false discoveries. Okay, so this is defined as expected proportion of false discoveries out of total discoveries. What do I mean by discovery? See, Rejection of H0 is generally of interest. In fact, that is how you frame your H0 and alternative hypothesis. Alternative hypothesis is something that you are interested in. So if your H0 gets rejected, then you say that you have discovered something. So expected proportion of false discoveries out of total discoveries means your FDR is actually defined as expectation of V upon R, right? But of course, if your R is 0, then this is not defined. So it is defined as expectation of V by R if R is not equal to 0, and it is defined as 0 if R is 0. Okay, this is your definition of FDR. It is defined as expectation of V by R if R is not equal to 0, and it is 0 if R is 0. Because if there are no rejections, then of course there are no false rejections also. Is it okay? Now from the three definitions, it is clear that PCER is expected V by G. R is number of rejections out of G, so R is always going to be less than or equal to G. Therefore, V by R is always greater than or equal to V by G, and hence expected V by R would always be greater than or equal to expected V by G. Okay, and when R is 0, at that time V is also going to be 0 because V is number of false rejections out of total rejections. So if there are no rejections, then no false rejections. So V is going to be 0 if R is 0. Hence expectation of V by G would be 0 if R is 0. So either these two are equal or this is the relationship. So we have proved that FDR is greater than or equal to per comparison error rate. Okay. Now, what about relationship between FDR and family wise error rate? That is slightly more evolved calculation. So we have to prove that FDR is less than or equal to family wise error rate. Correct? Family wise error rate is probability of V greater than or equal to 1, and this is expectation of V by R. Of course, if R is non-zero. So this is to be proved. Okay. So if R is equal to 0, then expectation of V by R is equal to 0, and probability of V greater than or equal to 1 is also 0, because if R is 0, then V is also going to be 0 almost surely. So in this case both are equal. Okay. Now suppose R is not equal to 0. There are two cases. Either G0 is equal to G or G0 is not equal to G. What is G0? If you go to this table, G0 is the number of true null hypotheses. Okay. So if all the null hypotheses are true, then what happens? And if some of them are true, then what happens? Okay. So if G0 is equal to G, then what happens? Then G minus G0 is 0. That is okay. But does that affect our calculations? So if G0 is equal to G, then what happens in this table is T and S have to be 0, because G minus G0 is 0 and G minus G0 is total of T and S. So T and S have to be 0. So V and R actually become equal. Okay. So if otherwise, even if you don't want to go to table, if G0 equal to G means if all the null hypotheses are true, then whatever there are rejections, all of them have to be false rejections. So in that case, my ratio V by R would be equal to 1 if R is not equal to 0, and it would be 0 if R is equal to 0. Right? So expectation of V by R actually becomes probability of V by R being equal to 1. Okay. So this is same as probability of R not being equal to 0. And we know that if r is not equal to 0 and v by r are equal, so this is same as probability of v not equal to 0. So this is same as probability of v greater than or equal to 1. So we have FDR as equal to family wise error rate if G naught is equal to G. Okay. And what happens when G naught is less than G? So if G naught is less than G, then V by R is of course less than or equal to 1, right? Because V is total number of false rejections and R is total number of rejections. So V is always less than or equal to R. And in that case, my FDR is expectation of V by R given R greater than 0, strictly greater than 0, into probability of R greater than 0, correct? Ideally, it should be followed by plus 0 times probability of R equal to 0, but that term is not going to contribute in expectation. So, FDR is this. Now, what we know is, if I call this V by R as say Q, then this is expectation of Q given R greater than 0 into probability of R greater than 0. And what I know about Q is always between 0 and 1. Okay. Q can never be greater than 1, this ratio. Okay. And this family wise error rate we know is probability of V greater than or equal to 1. So this is same as expectation of indicator of V greater than or equal to 1. Recall your result from probability theory. Expectation of indicator function is actually probability of the event of which it is an indicator. Or you can also think in terms of Bernoulli distribution. Okay. Now Q is always less than or equal to 1. Can I say that Q is always less than or equal to indicator of V greater than or equal to 1? Try to think. So indicator has two values. First value is 0. So when indicator is 0, it means that V is equal to 0. Because V is not greater than or equal to 1. So if V is equal to 0, we know that implies Q is 0. So in that scenario, I have 0 less than or equal to 0. So the inequality is satisfied. And when indicator is 1, of course Q is less than or equal to 1 because it is always less than or equal to 1. Okay. And now I can take expectation on both the sides and I can write expectation of Q is less than or equal to expectation of this indicator function. Okay. And expectation of Q is nothing but your FDR. Okay. So we have FDR as less than or equal to family wise error rate. Okay. So we have proved that in every case FDR is between PCER and FWER. So let me draw the picture again. PCER is somewhere here, FDR is somewhere here, and FWER is somewhere here. Of course, they are not like equidistant or anything. The distances are not at all indicative of the actual distances. What Bonferroni and SIDAC try to do is they try to decrease family wise error rate to be below alpha. So they try to put alpha somewhere here. So of course they control FDR also to be below alpha. But we have some FDR control procedure which tries to keep FDR below alpha. So you can put alpha somewhere here. So it is not as conservative as family wise error rate. So it doesn't inflate type 2 error that much. But at the same time, it does keep PCER and FDR in control. Okay. So what is the method to control FDR? Let us write down this procedure. We'll discuss the procedure, but we won't discuss how it controls FDR below alpha level because it is slightly quite complicated proof. So we will just study the procedure. So procedure to control FDR. The earlier procedures, Bonferroni and SIDAC, they are known as one-step procedures because you just do same adjustment for every p-value. Okay, whereas in FDR we are going to do slightly different things. So we first arrange p-values in an increasing order. Okay, and we'll use the notation of ordered statistics. So we will say p ordered 1 is less than or equal to p ordered 2 less than or equal to p ordered g. Okay, so p ordered 1 need not correspond to the first hypothesis. It is basically the lowest p-value. So this is most significant p-value and this is least significant p-value. So all the p-values, some of them may be greater than 0.05, some of them may be less than 0.05. Everything we are ordering. Okay. Then let P naught be the proportion of true null hypothesis. So basically G naught upon G. But we know that this proportion is in most of the cases unknown. So we generally work with a conservative value of P naught, that is 1. Why this is conservative? Because this is like worst possible scenario. If all the null hypotheses are true, then whatever we are rejecting is actually false. Is always false. So this is like worst possible scenario. So we work with this. So if we can say that even with this FDR is under 5%, then of course if some of the null hypotheses are true, then FDR is further less. Okay. Then let I alpha be the first value of I when starting from G such that Pi alpha ordered is less than alpha times I alpha upon P naught G. Okay. Let us write down the procedure, then I'll give an example with which it would be clear what we are exactly trying to do. Okay. Then the FDR control procedure says reject all those H naught for which P value is less than Pi alpha. Okay. Okay, some of you might have followed it, some of you might be completely lost. So let me try to give some example. Okay. So suppose we have 5 null hypotheses. Okay. And let us arrange their p-values in the ascending order. Suppose the p-values ordered are p1 is equal to 0.001, p2 is equal to suppose 0.015, p3 is 0.04, p4 is suppose 0.045 and p5 is suppose 0.06. Okay. And let us say that this corresponds to say second null hypothesis, so H2 naught. This corresponds to say third null hypothesis, this suppose corresponds to first, this suppose corresponds to fifth, and this suppose corresponds to fourth null hypothesis. Okay. Now we have to compute that quantity first. Okay, alpha times I upon P naught G, but P naught we are taking as 1, so upon G. So alpha is 0.05, I is the number. Okay, so here I is 1, 2, 3, 4, 5. Okay, this is I. So first number would be alpha upon G. So alpha is 0.05 and G is 5, so it would become 0.01. Next number would be 2 alpha by G. So 0.05 into 2 upon 5. So basically 0.1 upon 5. So 0.1 upon 5 means 0.02. Then it would be 0.15 upon 5 because 3 into 0.05. Okay, so this becomes 0.03. Similarly, this becomes 0.04 and this becomes 0.05. Okay, now we have to see from down which of the p-values are less. Okay, so what does the procedure say? Let alpha be the first I when starting from G such that pi alpha is less than that cutoff. Okay, so let us check from downwards. So here, is my p-value less than this value? No, here p-value is greater. Here also p-value is greater. Here also 0.04 is greater than 0.03. Here also 0.0, okay, yeah, here 0.015 is less than 0.02. So going from downwards, this is the first time that it is happening. So we say that we reject these two H0s. So we reject second and third, in the original setup, second and third null hypothesis. So these two would be rejected, others would be accepted. Now see, originally I would have rejected, without any p-value adjustment, we would have rejected these first four. 4 means second, third, first and fifth. All these hypotheses, because all of them are having p-values less than 0.05. But in the adjusted setup, we are trying to decrease the number of positives. So we are rejecting only 2. Okay. So this is a procedure to control FDR. All these methods can be done in R. There is a command p.adjust in R which can do everything. You just have to pass the p-value vector. It would give you adjusted p-values. What you have to do is you have to compare the adjusted p-values to 0.05. That's all. Okay, but you should know the theory. So that's why we have discussed 3 methods here. There are many more methods. But the important point to be remembered, multiplicity in testing of hypothesis is a very, very, very serious issue and we should never ignore it. So whenever you have too many variables and you are trying to carry out some sort of test, you should always adjust the p-values and only then you should focus on those null hypotheses which are rejected. Okay, only after adjusting p-values. Okay, so let me stop here. Thank you.